The second session is on fuzzy-based machine learning with application in temporal data processing. I've just covered about learning methods and issues specifically while processing the remote sensing data. So what different issues we can encounter and how they can be solved. Now I'm starting with this one, this fuzzy based machine learning algorithms with application in temporal data processing. So here we'll just try to understand what is image. If you see image, it looks like a chessboard and different colors. You can say false color composite. Actually, if you zoom and see further, you get a grids, row and column, and you have squares. If you see further, actually you see numbers at different locations. You have rows, you have here rows, and here you have column, and at any location if you see, you get number. So there is nothing color. The image has rows, column, which tells the position of pixel in an image because this is matrix form, and at that location you see number. The number can be going from 0 to 255, it is 8-bit. It can be 9-bit up to 511. It can be 10-bit, it is 1023. Then 11-bit, 12-bit, 13-bit, 14-bit, 15-bit, and so forth. You may have 16-bit. Sometimes you may get in some cases 32-bit also as a float value. So image, if you try to understand, is very, very important thing when we go for digital image processing. We should understand the image, right? So image is basically numbers arranged in the form of row and column, and there is no color. When you fire these numbers to color guns on a display device like monitor or any other display device, there you have color guns, and color guns get these numbers and they assign different color according to the value of that pixel value, and then you get the color once you mix all the basic red, green, and blue color. So this is a digital number, and this is the basic understanding of image. You can see on the remote sensing image also, maybe black and white. This is a full scene. You can take small scene. It looks here. If you zoom in, you get a black and white gray shades like a chessboard, which are pixels, the smallest element. And if you zoom further, you see numbers here at each pixel, which is arranged in the form of column and row. And then you have numbers, and these numbers are digital number. Digital image processing means doing manipulation to this number. If you just multiply these numbers by 2, that is also digital image processing, simplest process. And you can have mathematical expressions to modify these numbers. That becomes digital image processing. And a little bit more about remote sensing multispectral image. If it is multispectral like 5-band, so you will have 5 layers which are giving you integer values, sometimes float also, it depends. Generally they are integer, and it can go up to 8-bit, that is 255, 9-bit, 511, 10-bit, 1023, and so forth. And if you represent them as a feature vector, then the first pixel location comes like this: 35, 67, 150, 249. If it is 5-band, the first pixel can be represented like this, and it is 5 by 1 matrix. You can see before further processing the images, try to understand the information content present in each images. You can take an example. Nowadays there are different sensors at different resolutions. You can see the spot 5 sensor at 2.5 meter multispectral. You can see some stadium. This stadium, how it is appearing at 2.5 meter. Same stadium you can see at 0.5 meter in true color composite. This is your false color composite, and this is your true color composite. Same stadium. Here you don't see much information if it is true color. Same stadium, you can get the distinct information about the stadium. Second thing, if it is a spot 1 meter, spot panchromatic image at 10 meter. Now at 10 meter you can see from 2.5 meter to 0.5 you have seen, and if you come to 10 meter, same stadium information how it is appearing. You hardly see except the boundaries. Then if you take spot 1 to 4 multispectral, which was at 20 meter at false color composite, you hardly see a broadly tentative boundary. You can make it out. You cannot see spectator seats here so clearly visible. So it is very, very important at different resolutions. It can be spectral, spatial, radiometric, or temporal. So how the different objects, their appearance changes with respect to change in the resolution. So this you have to keep in mind, and accordingly, as per your application, you decide the remote sensing image to be processed to extract that object. So when we try to apply machine learning on Earth observation data, you can encounter some of the things, some of the points has to be considered, like data processing. Large memory may be required, because if you take like Landsat image, it is 7,000 by 7,000 pixels. Even if you take UAV image, I'm just trying to process the UAV image for some of the tasks through deep learning and machine learning. They have very large, they have very small pixel size, and with that the number of pixels are very, very large, and then that way the memory requirement is also very, very large. Then large training data. There are algorithms which can work with small training data, but there are algorithms like specifically deep learning algorithms with complicated models. They require large training data. Same way, like you can see the similarity, human being, the kid goes on learning for 12 years, 15 years on a different topic. So 15 years they are taking, a very huge training data is required. Same way for deep learning, a large training data is required. Then some of the algorithms may have generalization problem like ANN. Generalization means it can give you very good results for training and validation, but when you fire the testing data or unknown data, you don't get that much good accuracy. So that is generalization. So it is just like in a class, the student, when he's learning a topic and teacher gives a question for practice, he score very nicely on a practice question. When the student appears in an exam, he does not score so nicely. Exam is an unknown data on which algorithm has to perform, and that is called generalization issues. Then if you go more towards non-parametric algorithms, where there are a lot of parameters, so these parameters are free parameters, and these free parameters has to be optimized before we can get the best result. So sometimes the freedom is not actually freedom. Like the kids wants to prefer to go to hostel and study. They feel they get more freedom in the hostel. Nobody stops them. Mother goes on asking why you are doing this, why you are doing this. So that way they feel they're quite comfortable in the hostel. But in the hostel, they have to cook by themselves. They have to wash the utensils. They have to wash their clothes, and so many extra things they have to do. And with this, they get very less time for studying. But when they are at home, which they don't realize, everything is happening automatically. The food is coming to the table, the clothes are washed, the bed is ready to sleep, and they have to just study. But there they feel there is a lot of bonding. They are not free. So number of times when we go for advanced algorithms, what happens? There are a lot of free parameters, and these parameters has to be properly optimized so that we get the best results. So next, if we just see, I've already covered and little more, like fuzzy based algorithms. Why the fuzzy based algorithm for Earth observation data? The question, and the answer is to handle mixed pixels. They can handle the mixed pixels very nicely. To handle non-linearity, we can incorporate kernels in the fuzzy based algorithms to handle the non-linearity between classes. To handle noisy pixels, unwanted pixels can be handled. It can be due to sensors, the noise can be coming from the ground or on the image. Any class which we are not classifying, that is untrained class, and that becomes noise. So all these different type of noise can be handled through fuzzy based algorithm. They are capability to identify single class because they can handle the noise more nicely. Then they also conclude that they can handle the single class. I've given you example. If I'm willing, I want only vegetables, so I go to the market. My interest is to locate only the vegetable shops. I'm not interested to any other shops. So that means I'm interested to get only one item. Same way here, the algorithm is interested to extract only one class. So does all the algorithms capable to map single class? That we have to see the answer. Some of the fuzzy domain algorithms are straightforward. You can just give one training data of one class and you can extract that class, and other classes will not be extracted, and the algorithm will give you very high accuracy. Then we have to see the advantage of fuzzy based algorithm. They require very small training data. If you compare with deep learning, it is always there that we require thousands of photographs to train. Sometimes it is a myth, sometimes it is wrong statement. It's not always true that we require very large training data. In the deep learning algorithms also, it depends how our complicated algorithm, the problem is. Accordingly, we have to decide the training data to get the best result. Sometimes our problem is so simple, we don't require so large training data. But in fuzzy algorithms, it is always there that we require very small training data. That is a plus point, because collecting large training data from the field is not so easy. It consumes a lot of time and cost, and number of times it is not so easy to go every time in the field, like last more or less to be of 2 years. It is not possible to go in the field due to COVID. So there are so many factors there. So here just I talked about what is image and some of the issues and some of the plus points about fuzzy based algorithm. I'm not just favoring, you can really feel it in the coming slides, how nicely the fuzzy based algorithms are for mapping purpose. This slide I've already shown in my last session today. Just to recap again, the supervised method for remote sensing image, we are providing the training data, say for class water, agriculture and rock. And here if we apply any algorithm, since it is getting training data, so it gives you the output with labels of A, B and C. But here if it is unsupervised, you have just one image, say 3 band or 5 band, whatever it is. You apply the algorithm. You have to see that algorithm has very simple parameters which can be initially estimated, and they can be refined with respect to iterations, and you get the output as a clusters. Cluster 1 blue, red is cluster 2, green is cluster 3, and yellow is cluster 4. So here labels are missing. You cannot say what is yellow actually on the ground because there was no training data. You can see here same, I think I've just covered in the previous session. This slide also, you can just recap for hard. If it is 5 band data, it can be supervised or unsupervised. You get the output as a single layer, and here each one pixel is belonging to only one class, and you say it is hard output. But here for soft output, again same image with 5 band, you are applying any algorithm, supervised or unsupervised, but your output is not hard output single layer, but you have fraction of images. Fraction means less than 1. So that is stored in the layer. 0.7 degree of membership for water, 0.1 for vegetation, 0.1 for wetland, and 0.1 for soil. So these are degree of belongingness, or simple way it is called membership value. So question comes, why fuzzy based classifiers? When we have pure pixels, that means all the pixels are grasslands. So they are pure pixels. You can handle through hard classification of pixel level land cover mapping you can do. But if few pixels are water, few are grasslands, but some are mix of grassland with water. So there is a question mark what label to be given to these pixels, because these are mixed pixels. So these mixed pixels can be handled through subpixel, or nowadays soft computing or soft classification approaches, and in that category very one unique models you can see, the fuzzy based algorithms which can handle these pixels very nicely. So first one is FCM. This is the first basic classifier in the fuzzy domain. FCM, fuzzy C-mean classifier. This is the objective function U, and mu is the membership value, D is the distance, I is the input pixel which is going from 1 to n, J is the class which is going from 1 to C. So this is a membership value. M is a weight constant. M value goes from more than 1. M value should be more than 1, and it goes up to infinity. The role of M is it controls the fuzziness. Higher the M, higher the fuzziness you can see in your output. So if you partially derivate this function with respect to mu and minimize it, so you get this membership function. Somebody was asking in the previous session how to get the membership values 0.5, 0.2. So from this mathematical expression you get the membership values. So this is for a class mu ij, and this is the distance for a given class ij to the power 1 upon m minus 1, and divide by summation k is equal to 1 to c for all the classes for a given pixel, and this is the distance for all the classes we can find out in a given pixel to the power 1 upon m minus 1. So that way you can find out the membership value through FCM. It's a few advantages or few points about FCM. It is long computational time because it was designed initially unsupervised, but as I told you today, any algorithm can be used supervised or unsupervised. Initially this algorithm was designed unsupervised, but today you can use it supervised also. If you provide the training data, you can get the distance from the training data. You don't have to assume the mean value. Then sensitive to initial guess of unsupervised case. So if you are generally, as I told you, this was designed initially unsupervised, but today if we provide the training data, we can use it supervised also. So if it is unsupervised, it has to initially guess the mean parameter, but if it is supervised, we don't have to guess. Sensitive to noise, that means this algorithm cannot handle the noise because it follows 3 constraints. The first constraint says mu value, membership value, should be more than or equal to 0 and less than or equal to 1. That's the first constraint. Second constraint follows the probability rule type of thing. J is equal to 1 to C, and where mu ij to be 1. And third constraint does not have much meaning, and that talks about I is equal to 1 to n, mu ij more than or equal to 0. So this is just talking about membership values between 0 to 1. But here it says in a given pixel, if you are extracting 3 classes, the summation should be 1. So if there are 3 classes and you are extracting only all the 3, no problem, it will give you best result. But out of 3, if you are extracting only 2 classes and you have dropped the third class, so that class membership value will going to merge to the first 2 classes, and there with this the accuracy of the algorithm will drop. So here it is following the probability rule, and that's why due to this rule it cannot handle the noisy pixels. Okay. Next one, further modified version, Kelkar has given the possibilistic C-mean algorithm, and its objective function has been modified. This is the case of fuzzy FCM classifier objective function. This is a regression factor added in the FCM, and then it becomes PCM classifier. Here you see one more extra parameter eta, which controls the shape and size of the cluster. So how it works? The first, it initially calculates the mu, like FCM. It is similar to FCM, same function here, this one. Then in second step, it calculates eta, which controls the shape and size of the class. And finally, in third step, it calculates the final mu. Final mu is a function of eta and d with m. So advantage, clustering noisy data sample. So it can handle the noisy pixels very nicely. It cannot tell which are the noisy pixels, but it will not also allow to mix the noisy pixels with the class of interest pixels I'm looking for. Very sensitive to good initialization. Now here you can see in the first step, the first mu comes from FCM. So it is very, very sensitive that this mu should be initially initialized through FCM approach. Then second point at disadvantage, coincident clusters may result because the columns and rows of the typicality matrix are independent of each other. So here you may have some little bit overlap between the clusters. So that way you can see, but still the advantage of this PCM algorithm is it can handle the noise. You can use it, this algorithm, for mapping a single class of your interest. Third one, noise clustering. By the name itself, it is very strongly algorithm designed by Dave to handle the noise. The name is noise clustering, again unsupervised, and you can see its modified version of regularization factor. If you partially derivate this one with respect to mu value, and you get first mu like this, which is for class of interest, and you get second mu I plus C plus 1. This is for noisy pixels. So this clustering noisy data samples quantitatively. This means the PCM handle the noisy pixels, but it will not tell you where are the or how much is the noisy pixels. But in NC, it creates extra layer, and the extra layer holds the membership value of the noisy pixels. So it quantifies the noisy pixels very nicely. That's the advantage of noise clustering. It was again designed unsupervised, but we can use it supervised if we have training data. Fourth one, modified. Yes, again NC classifier, you can use it for even extracting single class. If you are extracting only one class, you will get an output, there is no issue. MPCM, a modified possibilistic C-mean, its objective function further has been modified, and it gives you membership value in 3 steps. First mu equivalent to FCM, then second is eta equivalent to PCM, and third is your final mu, that is from MPCM. So that way, first getting this, then this, and then this, we can get the membership value for each pixel for a given class. Clustering noisy data very nicely to fit the clusters which are close to each other. When the clusters are very close to each other, it handles the cluster, these types of clusters very nicely. It takes care the cluster should be compact. So all these things, the advantage of MPCM classifier compared to other fuzzy based algorithm what I've just discussed. So here just I talked about starting from understanding image issues of processing and remote sensing data, and then I shown you the different fuzzy based algorithms, their objective functions, and how to derive the membership functions. And these lines I goes on putting up. And you can see the output again for the Ponta image. You can see the FCC this time. This is Asan River in the area. This Yamuna River. This is Gir River. This is canal from Yamuna River, which is meeting to Asan Barrage. This is Asan Barrage, and its water comes to Yamuna again. So here again we have tried to find out the barren lands, agriculture patches, dense forest, and water body. which are having membership value from 0 to 1. Black means 0 and 1 means white. So the more highly that pixel is belonging to the class, it gets the membership value tending to 1. And you can see the difference realistic. In the hard, it will tell all this water. You will never know it is shallow or deep. But here, wherever it is deep, you get the pixel value tending to 1. Wherever it is shallow, it is tending to 0. And wherever is in between, you may get in between membership value between 0 to 1. So it gives you really true representation with respect to ground. The fuzzy is basically giving you closeness to the actual information present on the ground. So these are the outputs marked with the yellow, focusing with the yellow polygons. Then you can see the contextual part. I've talked about as in hybrid classifier. You can say we have tried to mix the contextual information in the basic fuzzy classifier. So what happens? We are adding the spatial domain as a contextual information through neighbor pixel information if you are adding, and this we have tried through MRF, Markov random field, as well as local convolution method. I just talked about it a little bit on the previous slides also. And what happens with this? It can basically remove the noisy pixels further, and it improves the accuracy 2 to 4% or sometimes 6%. What they do, they basically correlate with the neighbor pixels. Higher correlation, higher the contextual information it is present and incorporated in the base classifier. So this varies the correlation according to the spatial resolution and scale of neighbor or cultural regions. So according to the class, if there is a water body, agricultural land, they are more homogeneous, they have high correlation. The urban is very heterogeneous, they have less correlation. So that is the behavior of correlation with respect to culture or region. According to the spatial scale, when the spatial scale is less, pixel size is more, the correlation information will be less. As the pixel size is increasing, the correlation will increase in a given class. So here you can see agriculture has very high correlation, water body has very high correlation information, and urban has least correlation because urban is a very heterogeneous class. Then in the coarser spatial resolution, the correlation information is less. For finer spatial resolution, it is more. So as the pixel size is decreasing, your correlation information is increasing. And this we have tried, like if you see in the literature, people have tried correlation information through low pass filter as a pre-classified stage or at the post-classified stage using median filter. So very popular steps, people were using it pre or post-classification stage. It's mainly on the post-classification stage through median filter. But what we have experimented during classification using prior energy functions, can we apply this contextual information through MRF? And answer was yes. So here we can have the global post energy function, we have conditional energy, and here we have prior energy, which is adding the spatial information. This is adding the spectral information from the base classifier. We have taken base classifier as a fuzzy classifier, and here it is adding the spatial information, so that contextual information can be added in the output through Markov random field. So here you can see some glimpses of output. This is a list 4 image and the field photograph we have collected near to the dam. And when we have taken the output just with fuzzy, without contextual, you can see along the road there is shadow, and shadow is classified as water bodies. It's here also. But the moment we add the contextual information, you can see in this area that shadow has been removed so nicely. So that way we can remove these small noisy pixels and we can improve the classification accuracy. And this slide I have already shown you from DA and smoothing prior. Here you see more smoothing effect when we apply the smoothing prior, and through DA, discontinuity adaptive prior, the boundaries are preserved and you can see more detailed information. This also I talked about when we are adding the local convolution method. This is the actual raw input image, and this is the output of the wheat class. Wherever there is white, that is wheat class. And here just adding 1% noise, it is hardly affected, output is hardly affected. When there is 5% noise, it has a green dots, still output is hardly affected. How we do all these image processing activities, we do our own in-house tool called SMIC tool, which is capable to display image, to display images, false color composite, to collect the signature data in different modes, and apply all these algorithms through this mode. Now I will push up this second session towards temporal data, specifically for agriculture crop, and you can see the applications for specific crop stage mapping, crop insurance, specific vegetation mapping, and post damage assessment. Even in urban, you can see the area which has been converted from open space to building can be mapped that. So here you can see the really live examples, the experiments we have conducted through MTech and MSc students, or even rather PhD students also. But the first case you can see recently we have done it for mapping the transplanted paddy fields at specific date. Now you can see at specific date, it is not just mapping transplanted paddy field. We are trying to map at particular date what are the fields which has been transplanted. So we have experimented on a study area which is covering Ambala, Pewa, Ladwa, Kurukshetra, and Rador districts. Here you can see one example, one small subset. We have taken the 2 dates of pre-transplantation, that was on 19th of June and 29th of June. Then one image we have taken of 8th July, on which we are finding out the transplantation done. And next date, we were not having any optical image, so we have taken here 13th of July. So here you can see 2-3 things. One is multi-sensor approach. These 2 images are from Sentinel-2 data, optical image. This image is from Landsat. You can see its resolution is 30 meter. And on 8th July, we are finding out the transplantation done of paddy fields. And this on 13th July, we did not got any image in the optical domain. So here we are using the image from Sentinel-1, SAR image. So from 3 different sensors, Sentinel-2, Landsat 8, and Sentinel-1. From 3 different sensors, we are incorporating the data and trying to map the paddy fields. So that is one problem, to incorporate the multi-sensor data, here 3. And here we are able to get the paddy fields as a white patch, but we got one problem. There was a dry river stream which was classified as paddy fields here. So how to remove this? Because in the paddy, this river, how it is working, initially it was like a soil, then it was wet and due to rains, and then it was green due to grass. And same way in the paddy field, it was dry initially, then wet, filled with water, and then transplanted. So both were giving same signature, and that's why there was spectral overlap of this dry canal with the paddy fields. The question comes how to handle this. So what we have done in the same constellation of images 4, we have added 5th image of 6th March, predated image when the wheat was grown in that area. And now you can see that here, that dry canal has been easily removed the moment we have add the 5th dated image. And again, now you have 3 images from Sentinel-2, the 1 image from Landsat, and this image from Sentinel-1. So this is a multi-sensor approach, temporal data, and we can get the output. It is just like in real life, I give funny examples, but not funny, it's quite serious. Like Punjabi boy can marry a Tamilian girl. It happens, right? Intercaste. Same way here, can we use multi-sensor? The multi-sensor moment you use, the capability of information content increases. And that is very, very important to tap that information from different sensors, and very informative information, very accurately information with respect to ground we can extract. That's the motive for using this bi-sensor or multi-sensor approach. And here algorithm we have used CNN model, and you can see it's epoch with accuracy, behavior, and epoch with loss. And here you can see the structure: 128 convolution 1D, 64 convolution 2, max pooling, and dropouts. We have also experimented to have a hybrid approach, CNN with LSTM, which is a form of RNN. So here you can see the first LSTM layer and second LSTM layer here. And this is a structure what you have got as a best optimum structure for CNN LSTM. We were just trying to see how this hybrid layers behave. Little less output we received from this model when we compare with CNN. But nevertheless, we are just trying to curious to see how this type of hybrid approach models we can get, or can we work. Then in the fuzzy domain, you will really see one more good thing: heterogeneity within class. If you take a field of wheat, this field is not uniform. Somewhere the wheat plants are weak and somewhere the wheat plants are healthy. And due to this, within field, you have heterogeneity, and this heterogeneity degrades your classification results. So what we have done in the statistical classifiers, we are generating mean parameter from the training data, and that mean is used in the classifier, even including fuzzy classifiers. But what we have done, we have not considered that mean. We have considered each sample impact as treating each sample as mean. So this is not seen or used in machine learning algorithms as they has been implemented. You can find out from the literature they are using mean parameter from the training data, but here we have not used mean. I will give you the real, again, live example of in a class. The one teacher is teaching mathematics, and he says that, look, after the exam, my class has performed very nicely, and the mean percentage of my class is 80%. But you see, the student got marks from 60% to 90%, but the teacher says my class got average is 80%. But that 80% does not give you the complete holistic picture of 60 to 90% marks distribution. Actual marks distribution comes when you take the samples from the student, what marks they got. Somebody got 60, somebody got 75, somebody got 70, somebody got 72. So that these sampling really give you the marks distribution the class in a class the student got. So here what we are trying, we are not generating any statistical parameter, specifically the mean parameter. The mean may be good as a statistical parameter, but not gives you a realistic picture on the ground. You can take in the COVID scenario, government says the death is just 1%, but if you see the people, family really got affected, for them death in their family is 100%, and that has given a very drastic serious impact in the family. So same way here, the students or the samples gives you the realistic picture. So we are using these samples as mean. From this I can conclude you as management output also, like if there are total 10 employees in a company, out of 10, 3 are worker and 1 is a boss. So company runs according as per the contracts. So worker job is doing the task, doing the job per day basis, and the boss task is to get the contracts. So that is the actual boundary we define. Boss is boss, employees are employees, so they can't mingle. They have boundary of boss and employee. With this, what happens, that the company performance just remains 1%, because employees are doing job, boss job is to get the contracts. The 1%, how much contract he will get to run the company, to increase its profit. So other way around, virtually, if I apply the virtual concept, all 10 people can work as a boss, and all 10 people can work as an employee. It is true, it is possible, because with this what will happen, if all are virtually thinking they are boss, officially they are not boss, 1 is boss, 10 are 5 or 9 are employee, but unofficially, virtually they think they are boss. Then what happens? Everybody start thinking to get the contract. So with that, 10 times getting the contract increases. In place of 1 time, it is now 10 times. So that way the effect comes. Same way here, when we are using mean, it does not give you full distribution. If we use all the samples, that really gives you the actual representation of the ground. So here we'll see in the coming slide that effect. And you can see this is a forest patch. It is quite homogeneous. Still, it is not 100%. There is some homogeneity. There is some heterogeneity. And here in this open land, this is quite heterogeneous. Somewhere it is wet, somewhere it is dry. The sand color is wet and white is dry, and somewhere there are some other color patches. So it is quite heterogeneous, and this heterogeneity cannot give you very good results for classification. So here you can see heterogeneity within class, considering each sample impact not seen in machine learning as they are implemented. So what we have done, individual sample as mean approach. That means we are using individual sample as mean approach. In a company, if I give respect to every person, then my results in a company will increase. That's the meaning here. Individual sample as mean. So here, if we have, these are the samples, this the blue color. But if I calculate mean, mean comes here, which is going in the classifier. But we are not using mean. We are treating them, these sample as mean, which are going in the classifier, and that way the accuracy results increases with respect to handling the heterogeneity within class. So here you can see one example as an output from sentinel image. Again, temporal data we have used, and the study area you see, it is near to the Banasthali, surrounding of Banasthali Vidyapeeth near to Jaipur, which is a girls' renowned university. Here we have tried to map 3 classes. One is mustard crop, and for mustard you can see this was a training data, training field. And when we have tried to use this individual sample concept, you can see this field has came through fuzzy classifier as a homogeneous field. But same field, when this has been extracted while treating the samples as a mean statistical parameter extracted from the samples, this field has not came so homogeneous. It is very homogeneous. It was a mustard field, but not yet picked up by the algorithm to be as a homogeneous field. And you can see same other fields in an area. Here it is quite homogeneous, and here they are not. Then you can see for grass within the campus of Banasthali, this is a cricket ground, which is quite homogeneous, circular one. Here you can still see some white patches. And there is a parade ground which is hardly picked up as a grassland, but here this has been picked up as a grassland. And within campus, other grassland patches has been picked up very nicely. Here hardly this is a ground which has been picked up. And you can see outskirts near to the airstrip of Banasthali, there are few grasslands outside which has been picked up very nicely. But here, when we are using statistical parameter of mean, these fields has not been picked up. But when we are using individual samples, these fields has been picked up very nicely. Third class, you can see for wheat also, these are the 2 test fields. Myself collected the ground truth information. These fields has been picked up very nicely. But same fields, if you see here, not came so nicely when we are applying the mean concept. But when we are using individual samples, the output has came very nicely. This you will not see in the book because one of my PhD scholar is working, and his second paper is just coming in few days. It's already accepted with a few minor corrections we have to do, which is already done, and maybe it may be ready in the coming 15 to 1 month online. And this is really one more example of UAV images. I told you UAV images are also huge because pixel size is very small. So this is a greenhouse. Within greenhouse area, through UAV flying at 1 meter or 2 meters, we are trying to map the weed portions so that we can extract how much is the weed portion in the area. So here the weed is quite heterogeneous, and we are trying to map the first cauliflower, and if we subtract the cauliflower area, we can find out the weed area. This is just a preliminary study we have done, and I'm trying to work with one of the PhD student who is in Italy, and they have this project. I'm trying to technically assist to him, and he was my MTech student at IIRS Dehradun. Nevertheless, I'm interested to process this data of which is coming from UAV, and you can see as a preliminary result through fuzzy based with using individual sample as mean, you can get this output. You can really see homogeneously this cauliflower field has been picked up. If you see the cauliflower field itself, it is quite heterogeneous. There is a white color here, the white veins. Somewhere it is dark green, then it is very light green where it is young. Somewhere you can see a lot of shadow. Within cauliflower, you can see a lot of shadow here. Yeah, so due to the shadow portion, due to variation in the pigment on the leaf, and somewhere hardly any pigment, somewhere it is very young. So this cauliflower itself is a heterogeneous object, and what we have developed, the individual sample as mean concept, can really handle the heterogeneity, and you can see in the preliminary result nicely this heterogeneity has been handled. We have taken very limited training samples. Now we have increased the training sample. The moment we increase the training samples, you can see this heterogeneity handled more nicely. We are just going to experiment because we have just solved that issue, and you can see the individual cauliflower how nicely, and still you can see small shades. These shades we can easily further remove if we add few samples in these locations, and we can easily remove these portions also, and we can label them as cauliflower. And moment we train the algorithm with more samples, we can go on extracting these cauliflower plants very nicely in the complete image. Next example I'm showing you for sunflower crop, which was we found a few pockets near to Dehradun in Haryana state, as called Shahabad area, which is under the district of Kurukshetra district of Haryana. Here we have tried to use the temporal data, and we have tried to extract single class, that is sunflower. So here again, this is our in-house developed technique to process temporal data for a specific crop or specific class. We can try CBSI, class-based sensor independent. So this is a modified version of NDVI. NDVI was developed in 1973, but it was very nicely acceptable. Still we found that there are so many sensors, and the person should know which band, where is NIR band, where is red band, and to enhance. So what this CBSI does, it selects the suitable bands so that we get the maximum enhancement. That is the use of class-based sensor independent. So class-based means the class can be water, class can be soil, class can be of any crop or forest, it can work. Sensor independent means the data can be from any sensor. It can be Landsat, it can be hyperspectral, it can be UAV, it can be Sentinel or airborne. It can select the suitable bands, and it will give you nicely enhanced NDVI approach, or we can apply other formulas in the tool given. So what we have done here, we have the sunflower crop is generally sown from Feb-March, and it is getting harvested in May and June. So we have taken the image from 21st March to 30th of April with one of the PGD student who has done 3 months, and she was able to publish the work in Indian Society of Remote Sensing Journal. You can see this paper there, and you can see these images. And applying this NDVI approach, the spectral information of the sentinel data has been reduced, but time domain information has been maintained. So you can see the sunflower pigment maybe growing like this with time. So this temporal curve, this temporal phenological changes we can incorporate, and you can have subclasses here like early sown of sunflower, middle sown of sunflower, and late sown of sunflower. You can map, and you can see some overlap also between S1 and S2. And one more application we have done in Patiala regions twice in last 2 years for mapping burned paddy fields, stubble burning, right, in the Patiala region surroundings using sentinel data. Here, what we have done, we have taken the pre-burning image and post-burning image, just near to the post-burning image. So here in the pre-burning, the field is dry biomass of paddy, and in the post-burning, it is burned field. So just 2 data. Now we are applying the NDVI, and then we can take the NDVI temporal data in the classifier, which is capable to map single class, and we can get the burn paddy fields. Here you can see the green patches are the burn paddy fields at particular date. You can see nicely at what interval we are able to map. Starting say 20th of October 2018, that was the first study we have done. In 18 and 19 also we have done study. On 20th of October, we are able to map the burn paddy fields very less. Then 25th of October, it was increasing. Then 30th of October, it was further increasing. Then 9th of November, and then 19th of November. Around 5 to 10 days interval, it was possible to map these burn paddy fields. And this is very good information specifically for government, where they want to restrict, they want to keep a watch, and they want to find out which farmers are doing these activities. So with these technologies, they can easily geolocate the fields which are burned. You can see graphically with the date wise the burning: 30th of October, 9th of November, 19th of November, then again 20th of October, 25th of October. Every around 5 days to 10 days, it was possible to find out the burn paddy fields. You can see the full image what we have processed, and in that image you can see the distribution of these burn paddy fields at different time here. And this is again as an input data to estimate in a given district or from a given state, if the burning is happening, it is a well-known problem nowadays. It is quite in news always in October and November, that from a state, can we estimate how much pollution in the air is coming up due to burning? And we can restrict once we are able to, government can identify these fields with geolocations, and they can really take some serious actions. The moment they take serious actions to some of the fields and the news spreads, then other farmers will really think about that they should do this burning or not. Previously, for Triveni sugar mill, we have done to map the sugarcane catchment fields. Basically, for a sugar mill, they in a catchment of say 16-kilometer radius, they have always keep a watch that how much fields are for ratoon and how much fields are for plant. Plant is a first-year crop and ratoon is a second-year crop. Sugarcane is not a crop. In sugarcane, actually, they keep a watch which fields are for ratoon and which fields are plant. So can we do that? Because ratoons are ready by 6 to 7 months and plant crop takes around 8 to 10 months. So here it was possible for Triveni sugar mill near to Dehradun in Saharanpur district, we were able to map the plant fields and ratoon fields at AWIFS image. Later on we tried with list3 image also, and you can superimpose these outputs. You can bring it as a one output. Here you can see the green is plant fields and red one is the ratoon field of the sugar cane crop. So the sugar mill people are interested to know how much is the ratoon, because which will come first by October onwards, and the plant crop comes later. So they should have a estimate to know the catchment which is sufficient for their mill to give the feed. They always annually they do study that how much is the ratoon and how much is the plant in that area. So they can keep they are satisfied that much sugarcane catchment is sufficient for them for ratoon and plant. If not, they can make some further alternate arrangements. This again for paddy fields we have done date-wise mapping, say, and we are able to distinguish the water bodies, because when the paddy is transplanted, all the fields are flooded, and all the agriculture fields where the transplantation has to be done, and the water bodies in the area appears to be water body. But we are able to map the fields on 24th of June. We are able to map the fields by 10th of July, and we are able to distinguish the existing water bodies in the form of canal, river, or water ponds near to the radar area. Long back, I got our proposal was accepted, and we are able to got the 2-date data from Worldview 2 of surrounding of Muzaffarnagar district. You can see by 3rd of March 2010, and 12th April 2010. And this was the harvesting stage of Rabi field, Rabi crop, specifically the wheat. And you can see with the 2-date data of near to harvesting, we can find out which fields has been harvested. So you can see this is a wheat field ready for harvesting, and now it has been harvested. So once we map this using this temporal information, we were able to map the wheat fields which has been harvested. The wheat field which has been harvested got higher membership value tending to 1, and other fields got more or less tending to 0. So here you can see these two fields looks to be crop of Rabi, but when you see in the output, these are not the Rabi crop, these are something else. So you can easily distinguish, because this is 2 meter pixel size, you can at the boundary level with the naked eyes, you can easily see the results, how the results are coming up. We have done for list 3 image for wheat area from using image from 21st of November 2008 to 11th March. This is a period when the wheat Rabi crop is grown, specifically the wheat one. And this is a preliminary processing through TVI. And these are white patches here. You can see wherever there is white, that means the membership value is 1, tending to 1 for wheat fields. This was in Udham Singh Nagar near to the Kashipur region. We were able to map using list 3 data. And yeah, it's this from AVIF's image rather, not list 3. We have done for list 3 also later. You can see further examples with one of the PhD scholar for cotton crop mapping in Aurangabad region, because there's a belt of cotton crop, and crop starts say from May, and that get harvested up to say March. So it has taken a cycle from May 2010 to March 2011, and here you can see the fields were mapped, which were cotton fields, while using this temporal data. We have done for forest also, deciduous forest in the Shivalik Hills. Here you can see the deciduous fields, the forest fields has been mapped. We have also tried, once we got the Formoset data, temporal data again, and we have tried to add the Landsat data to keep the concept of bi-sensor concept, or dual sensor concept, near to Haridwar, towards Nazirabad, east side of Haridwar. So these are the Formoset image. We have tried to map the paddy fields, and can we separate with the water bodies? There's a Ganga and the canal, some of the canals coming from the Ganga river. So yes, we are able to map the paddy fields, and we are able to separate them with the existing water bodies like Ganga river and the canal. And we are able to add the Landsat data wherever the Formoset image was not available. So we can have the dual sensor concept is also possible. Secondly, last year we have experimented that in urban we go for built-up change detection. So in the, if we have say 6 years data, 6-year time gap data, 10 years time gap data, we try to map how much built-up has been changed. So built-up does not give you the information up to building level. From Sentinel-2 images of 2 date, one was October 2013, that was from Landsat, and next image from in October 2019 we got from Sentinel-2, because Sentinel came in 2015 onwards. So using these temporal dates of 2 date, it was possible to map not built up change, it was possible to map the building footprint. Now you can see in built up change detection, can change be mapped at building footprint level. That means in October 2013 there was an open land. In October 2019 the building has came up. So can we map this area which has changed from open land to open area to building level at 10 meter? Spatial resolution answer is yes. Used 2 date images of 2013 and 19 from Landsat and Sentinel-2. You can say dual sensor concept we applied, and we applied the algorithm fuzzy based MPCM machine learning algorithm, and we got the very good prominent results. And this work was published in SN Applied Science Springer Journal last year. So here you can see one complete image of covering Dehradun, we have taken one training site at Baruwala colony, which was used as a training site where we can see large buildings available, and other areas like main Sabji Mandi of Dehradun, ISBT of Dehradun, Kalidas Road, which is our campus region, and Doon University. So these are four areas we have taken as a test site to test the results, unbiased results. Here you can see for Kalidas itself first, the outputs, how it has came up. There was Shivalik apartment on the Kalidas Road, Vikram Sarabhai hostel within our campus, Golden Jubilee hostel, and stand on Bangla outside the main gate, and the Meridian apartment heights or the Meridian Heights apartment were easily mapped. This is your Shivalik apartments on the Kalidas Road. This is a Vikram Sarabhai hostel B, where I always daily play the badminton. So it is a well-known place to me. Last year this building was ready, and the C building is your Golden Jubilee hostel. It came around 2-3 years back. Then D is your outside main campus. They have changed the they put an extra tin roof building on the top of the building to protect from seepage and extra things. And there's a Meridian height apartment. So all these buildings we can easily see on the ground, and we can easily see this has been mapped. We have experimented to see the NDVI differences. There we can see only the NDVI difference, but we cannot map the building level changes. We have applied with the post classification change detection. There we can see only the build up change, but we cannot map up to building level these changes. So that is the beauty of the approach what we have proposed through fuzzy based using this temporal data. You can see for Baruwala colony, which was the actually training site, there is a large big buildings, and these buildings has been mapped very nicely on our approach. But on the post classification stage, we were not able to map the building level changes. Or in the NDVI difference, we can see the NDVI difference, but we cannot see the NDVI difference, which can tell that this is the building which has came up in the area. And we can correlate these changes on the Google Earth. On 2019, these buildings came, and these buildings were not present in 2013. Then at the Doon University, which is an old one, around 10 or 12 years back, but 2 buildings came up in this area within the Doon University campus, and these buildings were easily mapped and checked. Then at Sabji Mandi area of Dehradun, there are surrounding to Sabji Mandi, lot of apartments has came up, and we are able to map these new apartments through this approach in this Sabji Mandi region. Plus for ISBT is an old one, which is around 15 years old, maybe more than that. But near to that, there is some mall and offices came up. Can we map these buildings? Yes, we are able to map these buildings very nicely. Then long back, I just co-guided one PhD from IIT Roorkee. Can we map the post-earthquake damage assessment? Specifically for Bhuj area, it was experimented to map the liquefaction area. So answer was yes. If we take the pre-earthquake dated image of say 4th of January 2001, and then 29th of January, the earthquake occurred on 26th, but we have taken the post-earthquake image of 29th. And here you can see the red patches are the liquefaction area. And this was possible to separate the existing water bodies in that area. We have also experimented for, this is again for Bhuj area, using different satellite. This from IIRS 1D, this from again from IIRS 1D, and this was also from IIRS 1D, but we have applied different algorithms like PCM, which is capable to map single class, NC, which is capable to map single class, and again PCM and NC with different approaches. Here, same student has also experimented for Balakot earthquake, which came in 2005 and 6, and he was able to separate damage area, damage settlement area, and landslide, because the landslide damage built up, urban damage and urban undamaged, they will all give you the same reflectance on the single image. He has taken pre and post date image, and he was able to map the urban damage and urban undamaged area. You can see it was 80% damage was there. So this is the red patch, which was urban damage, and this is the blue one, urban undamaged. And you can see the landslide also. This is your landslide portions which was occurred in the area. So for temporal, what we have done a specific tool modification in the PCM where with 4 steps user can extract the single class, where we can load in the first 2 steps we can load the images. 3rd step we can create the intermediate indices process, and the 4th stage we can apply the classification. So here we don't require much expertise. We have to just load the images without knowing much, but we should have temporal images. And this is the first step, loading the image. Again, second image, loading the other temporal images. Then here, these are the settings we can do for training data has to be provided with a click or manually method, or NDVI by which formula. And we want a single sample or multiple samples for the same class. All the settings we can do. And then we want more samples within the same region. As a region coding approach, we can apply to get large number of samples from the algorithm itself as a region growing. And then your 3rd step comes to save the indices, and 4th step comes for selecting any of the one classifier to get the output. So this is a 4-step approach, and we can get the output. So this all, yeah, I'm again reaching to the last slide, and I will show you again the book Fuzzy Machine Learning Algorithms for Remote Sensing Image Classification. So today, this is I reached to the second session as the last slide. Thank you all for listening. And